Shane Picard with another geometry lesson, talking about similarity in right triangles. Start with the right triangle similarity theorem. It says the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. Okay, what exactly does that mean? Let's take a look. Here we have a right triangle, and the theorem talks about altitude to the hypotenuse. Well, the hypotenuse is down here. We know that because it's opposite the right angle. So the altitude to the hypotenuse would be right there. That's the altitude to the hypotenuse. So we have the altitude to the hypotenuse of a right triangle divides the triangle into two triangles. When we draw in this altitude, you can see there are now two additional triangles. So we have, in a sense, a total of three triangles. There's the original triangle, and then there are two new triangles when you draw in that altitude. The theorem says that each of these triangles, we'll call them triangle 1, 2, and 3. The theorem says that each of those three triangles are similar to each other. So this small triangle is similar to this medium triangle, which are both similar to this large triangle. How do we prove it? It's simple, actually. When we look at this right triangle here, notice that each of the triangles has a right angle. The medium triangle, which we've called number 3, has a right angle in it. And the small triangle, which we've called number 2, has a right angle here. And if you look, the original triangle has that right angle right there. All three triangles have a 90-degree angle in it. To prove similarity, we'll look at common angles between the triangles. So when I look at this vertex down here, that vertex is a vertex in the small triangle. It's also a vertex in the large triangle. And so, because that's a common angle to those two triangles, by angle, they are similar. Likewise, if I look at this vertex over here on the right, that vertex is common to the medium triangle and also to the largest triangle. So again, by angle, those two triangles are similar. Therefore, by angle, all three triangles are similar, and we have the right triangle similarity theorem. We need to take a quick detour and talk about geometric means. You may have already discussed those in a prior lesson. What does a geometric mean? In a proportion, A over B equals C over D. B and C are the means. They are the means. A and D are referred to as the extremes. It may be easier to remember if you write it out this way. A is to B as C is to D, and remember that the two in the middle are the means. Proportions in which the means are equal occur frequently in geometry. If the means are equal, then we can put a single variable in to represent the means. So it might look like this. For any positive numbers A and B, the geometric mean of A and B is the positive number x such that A over x equals x over B. So you see here we have the means, x and x, they're equal. We call that, in this context, the singular geometric mean. So we can find the value of that mean if we know the values of A and B. How do we find that value? We cross multiply. X times x is x squared, and A times B is AB, and we take the square root of AB. X equals the square root of AB. Notice that there. Let's look at a very simple example to get an understanding of what a geometric mean is. Consider the numbers 1 and 100. And we'll ask the question, what is the geometric mean? To find the answer, we're asking what number can be set into this proportion accordingly, such that 1 is to x as x is to 100. So to solve this, we'll cross multiply. X squared equals 100. And then take the square root of both sides. X equals 10. So 10 is the geometric mean. Note that I can multiply 1 by 10, of course the product is 10, and multiply 10 again by itself, and I'll get this product 100. Notice also that it may be helpful to contrast this with something called the arithmetic mean, which most people are familiar with. When we talk about the arithmetic mean, we add these numbers together and then divide by the number of terms. So we would end up with 50.5. A lot of times we call that value the average. The geometric mean is distinguished. It has more of a multiplication essence to it. And so we have the multiplication of the two numbers, 1 times 100, and then the square root of those values. And that is 10. Notice the very obvious difference between the two means. This is arithmetic. This is geometric. Look at a couple more examples. Find the geometric mean of 4 and 18. Very simple to set up. 4 over x equals x over 18. We cross multiply. X squared equals 4 times 18. And then we need to take the square root. X is equal to, the square root of 4 is 2. There's a 9 in here. And of course the square root of 9 is 3. And we're left with the square root of 2. So x is equal to 6 square root of 2. And that's the answer there. Good, one more. Find the geometric mean of 15 and 20. Set it up the same way. 15 is to x as x is to 20. We cross multiply. X squared equals 15 times 20. X then is equal to the square root of 15 times 20. 15, of course, is 3 times 5, and 20 is 4 times 5. So we've got 5 times 5 times 3 times 4. So the square root of 5 times 5 is 5. Square root of 4 is 2. And we're left with the square root of 3 inside the radicand. So x then is equal to 10 square root of 3. That is the geometric mean of 15 and 20. So that's how we find geometric means. Let's come back off this detour back into geometry for a moment. How do we actually apply those concepts in right triangles? I have to introduce these two rules called the corollaries, Corollary 1 and Corollary 2. They are some of the most confusing corollaries in a high school geometry course. So after I introduce each one, I'll also give you a parenthetical that hopefully states it a little bit simpler, although we need to be careful when we do that. Corollary 1 says, the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Here in the parenthetical, you can see it says the altitude is the geometric mean to the segments of the hypotenuse. What does that mean exactly? It means if we have a right triangle and we draw in the altitude, then this altitude is the geometric mean of these two segments here. We'll look at an example in just a minute. Second corollary says the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the adjacent hypotenuse segment and the length of the hypotenuse. That very well may be the most confusing thing I've said all day. I hope it is. How could we put that into a parenthetical? Just clean it up a little bit, make it a little easier. As follows. Each leg is the geometric mean to the adjacent segment and hypotenuse. Let's look at a problem and see if we can understand that a little bit more easily. To solve for x and y, here's a right triangle. And we can see that the altitude has been drawn in as indicated by the right angle here. And we know that the segments of the hypotenuse are 4 units and 5 units respectively. And we're trying to find x and y. We'll solve for y first, since it's probably the easier of the two corollaries to apply. And in this case, y is actually found by applying the corollary number 1. What does corollary number 1 say? It says that the altitude is the geometric mean of the two segments of the hypotenuse. That means that 4 is to y as y is to 5. Notice that the altitude is the geometric mean. 4 is to y as y is to 5. So we solve this by cross multiplication. Y squared equals 20. And therefore y is equal to the square root of 20. Probably know that there's a factor of 4 in there. And so we end up with y is equal to 2 square root of 5. So y equals 2 square root of 5. That's the answer there. What about x? How do we find x? The corollary to find x is a little bit more confusing. It says that each side is the geometric mean of the adjacent segment and the hypotenuse as a whole. In other words, 4 is to x as x is to 9. This leg is the geometric mean of this segment and this hypotenuse. Applying that rule, we can see that 4 is to x as x is to 9, which means that x squared equals 36, and x therefore equals 6. So we can find these values pretty quickly, understanding that there's some similarity that happens with the right triangle. Let's do apply corollary 2 one more time. Let's suppose that we need to find this value over here, z. Let's take a look at that. How do we find z? Notice that the corollary number 2 applies on two sides of the triangle. We can apply it over here, and we can apply it over here. It says that the leg of the triangle, z, is the geometric mean of the adjacent segment and the hypotenuse. So we cross multiply. Z squared equals 45. We know that there's a 9 in there when we take the square root of both sides. Z is equal to the square root of 9 times 5. And so Z equals 3 square root of 5. So that's the value. That's similarity in right triangles. Make sure you work through a few example problems. If you have any questions, as always, please send me an email.